So today we'll discuss very important topic, which is AES or AES cipher. Okay, and this is a cipher AES which is used mostly today. If assume that you are sending data from your machine to wherever, at least 50% times you are using AES or even more than that, because this is the latest standard for secure communication. Of course, there are other protocols also. In addition to this, you are going to use them as well. And this is, of course, symmetric. And we'll see why we use symmetric most of the time. Because it's fast, as simple as that. Okay, so please ask questions if you don't understand anything, because there will be a lot of questions in the exam. Okay, I will ask questions from something that I'm teaching, and I will also ask questions something you're supposed to read by yourself and learn. Okay, these are the references. Mostly I have used two references, two places. First, of course, is University of Berkeley, University of California at Berkeley, CS161. And second is the beautiful book and lecture by Professor Parr on crypto. This book is only on crypto. Okay, and advanced encryption standard or AES protocol. You can go through this video. It's lovely video. I've just 2 times have gone through this video and found it extremely good. Okay, so please go through it as an exercise. All right, so this is all we have completed so far. We are into symmetric encryption method, and last class we have studied something called DES. Okay, so this is a block cipher called DES cipher. Okay, today we'll again repeat what DES is, and then because we'll take some concepts from that, and then we'll go on to study AES. We'll complete AES today. Okay, so this is where we are. Their ciphers or encryption are basically encryption and decryption put together, are of mainly two types, symmetric and asymmetric. We are right now into symmetric part, and then there are in symmetric also there are two types of ciphers. First is block cipher, second is stream cipher. Block cipher is most popular. And a stream cipher we study, it has also used in mainly streaming bits. And when you don't have too much time to do encryption, like you are streaming a movie or whatever, then you can use stream ciphers. Block cipher, a very important property is that whatever be the input in terms of zeros and ones, note that everything in the world, digital world, is finally converted to zeros and ones, whether it's a file, movie, or video, or whatever. So you have zeros and ones that define any object, and then it could be of various lengths, but when we are encrypting them, we are splitting that into blocks of fixed size, and that blocks is transferred into encrypted block. Okay, and then we combine all these and concatenate all these to create one encrypted data, right? So we just concatenate, put one after other. All right, so this is the concept. Now we studied yesterday that there are two very important functions in encryption and also decryption, right? Primarily encryption. Decryption is just inverse of encryption. So and this was proposed by Claude Shannon, one of the very famous and great scientists. And then two functions are confusion function and diffusion function, or confusion operation and diffusion operation. Okay, confusion is by you confuse something. If you look at it hides the relationship between key and ciphertext, and this is done with a substitution function that we have studied yesterday. And second is diffusion. Diffusion means that even if in input there is a 1-bit change, then in output there will be this 1-bit change is impacting will impact multiple bits. Okay, all right. So now Shannon said that just doing confusion operation, diffusion operation once is not sufficient. So you will have to do many confusion and diffusion operations, right? And then we'll get the end cipher or product ciphers. So this exactly is shown here. You have a block of data, you diffusion, confusion, then second time diffusion, confusion, do this multiple times or a sufficiently large number of times, and then you get text encryption. And this property says here that single bit flip will result in multiple bit flips in output, and this is because of the diffusion property. We want to achieve this property. We want to design this cipher in such a way that it should have diffusion property, right? I mean, a single bit change may result in multiple bit changes in unpredictable way, right? Of course, these are all deterministic, but for an outsider like Eve, will not be able to make out what changes are happening. Okay. All right. Okay, let me switch off video. All right. So this was the DES. Now note that this consists of input is or block size is 64 bits, and then key size of 56 bits. Now many people question this, why 56? It's not 2 raised power x. Okay, but that's how it was. Okay, and then at the end, after encryption, we get a ciphertext of 64 bits. So 64 bits are transformed into encrypted or after encryption or encrypted version of plain text. Okay, that we call it ciphertext. Very clear? Okay. All right, so you can see that input is a block of 64 bits, output is also block of 64 bits, key is 56 bits. Now this DES, if you look the internal structure, it consists of multiple rounds, right? Okay, and it happens to be here in case of DES is 16 rounds. In each round, what we are doing, that we'll see. So there is initial permutation and the final permutation in between 16 rounds of some function. And that function that we see is this one, right? This function, which is essentially split 64 bits into 32 and 32 left half and right half. And then we take key, initially 64 bits. From that we generate a sub key which is of 48 bits. You can see it. Let me expand this diagram. 48 bits of key, sub key we get. Okay, and from this 56 we after transformation we continue to get sub keys which we'll use in each round. So in this round we are using sub key K1. Now these are all deterministic algorithms. Every time it will generate the same sub key depending on the value of the key. If keep the same key, value of key, you do encryption for the second time of the same plain text, you'll get the same sub key. Okay. Then there is then you take this 48 bits and then you use these 32 bits that are coming from right side, and then F function is applied to these two inputs, and the output is of 32 bits which you do XOR with the left side of data, and then we swap this and so on, right? So now you can see that on the left side of data is encrypted or transformed rather, we'll say, and right side of data remains as is. The next round we'll do it, this data will get transformed and so on and so forth, and repeat this 16 times. Okay, and then do the final permutation. After 16 rounds are over, do this final permutation, and then you have ciphertext, which is Y. Any question? No? This is what we have studied yesterday, and this network or this functionality we call a fiscal network. Okay, these two diagrams talks about initial and final permutation. Nothing great about it. First, for example, first bit becomes 58 bit, second bit becomes 50 bit, 50th bit, and so on and so forth. There's nothing great. And then we have seen here there's something called f function. Okay, so we see that the right half is coming here, which is 32 bits, because overall block is of 64 bits, divided into is 32 bits. Now you'll have to key expansion here. Sorry, the expansion of 32 bit into 48 bits by some expansion function. Take key of 48 bits, and then you have, after XOR, you have 48 bits available, and then split into how many? 8. So this 48 bits, you create 6 bits, 6 groups of 8 groups of 6 bits. Okay, so this first group, second group, third group, and so on, and then perform S function into it, with substitution function. Look at these 6 bits. Okay, these are the 6 bits, and transform this into 4 bits. How do you transform this? Using some substitute these 6 bits by 4 bit, and then using some table. Now, how this table is designed, etc., is a work of crypto. Okay, so our cryptographers have designed this, right? So now one such mapping, I'm sorry, this is expansion function, and this is substitution function here. So 6 bits are coming in, 4 are going out, and then this numbers, right? So basically what you do is take these 6 bits that are coming from you, for example here, and then look at the first bit and the last bit. This first bit and last bit becomes 1 1. Okay, that defines 4th row, and remaining 4 bits in between defines a column number. So there must be 16 columns. So there are 16 columns corresponding to this. So basically, and this is because this is a table which is statically defined. So you take now 4th row and 3rd column. So this first, second, third, okay, and the 4th row 0, 1, 2, 3, or first, second, third, fourth. So basically you take 0, 8. Okay, so replace this number by 0, 8. And then you have how many bits? 4 bits. So 0, 8 becomes 1, 0, 0, 0. And so on. Do it for all, and so on and so forth. So now this becomes one round. And do this 16 times, and finally do the permutation, and you get the output. All right? Any question?
Sir, the key was initially decided to be of 56 bits, but now it has become 48, like we have transferred.
Yes, because you are generating sub keys out of that.
Okay.
Initially, actually 64. Basically, algorithm says that use 56 bits, but actually input is always 64. Take out 8 bits out of that. Okay, that and then remaining 56 use, and each round you generate out of this 56 48 bit key, which you use in fiscal whatever, or f function. Okay, so this is the method. So you create this kind of, how do you generate that? Of course there's a key generation function which you'll not study. Okay, so you can, it's called key schedule. Okay, if you go through this book, it's a wonderful book on crypto, please go through it, or go through Professor Par's video lecture, you'll understand that. Okay, so this is the key schedule, how we generate it. Okay, sub keys, right? So you see here 48 bit key coming in the first round. Similarly, in second round, you will also get 48 bit key, and so on and so forth. What functionality you are doing, you have some rotation or whatever, bit rotation, you please go through the book. Okay.
So this means the key used in each round is different. Like,
Of course, yes, that's the purpose, right? But this is a deterministic again, it's derived from the same key. So it means that suppose your key of 64-bit is whatever you say 0101 whatever. Okay, so next time you do encryption, you have encrypted once, okay, and next time you do encryption you get the same subkey. So this whole algorithm is deterministic. Okay, only then you can apply inverse function to get back the original thing that you have encrypted, right? The original plain text you get. Now the question you may ask, how does it work then? If it's deterministic, everyone knows the algorithm. But Eve, who looks at the Cipher text, cannot make out what exactly is happening. Now she will try to inverse it because she knows all this algorithm, right? But how can she inverse it until she knows the key? So key has to be known. But but there are two important things. That first is, as we discussed earlier, we are doing confusion by substitution method. And then second is what? Second is basically spread the bit out. What's the word we use for that? Diffusion. Okay. So diffusion you do by this, gives you confusion. The diffusion is by what? XOR function mainly, or permutations. This initial permutation in the or permutation at the end gives you diffusion. Okay, all right. Okay, all right. So now let's move on to AES. Now, what was the reason DES was not? DES is still in use, right? We'll look at the reason for that. Before that, there's history. In 97 or 2000, it means that this AES is not very old, about 20 plus years old. NIST, which is organization in US, thought that this DES becoming old because ultimately breaking of any algorithm depends on what kind of computers you have, because you are going to use the brute force. Okay, now this AES also can be broken if you have quantum computers. Okay, all right. So now DES they thought is not good enough, and the key size is also small. So they say that all right, let's make this 128-bit. Key size is sorry, block size becomes 128. Key size is minimum 128. Okay, and let's make very open algorithm. Now note that DES was initially proposed by IBM, and they kept the design secret for very long, and only after many years it became public. Now what happens is that when something is, as we discussed earlier, something is not public, it's generally easy to break it because somewhere or other it leaks out. Okay, and nobody can find fault in DES, right, or any such algorithm. But when AES came, it was open design, right? There was challenge posed to everyone that come out with the DES required, and they gave the requirements. Okay, then a lot of people proposed this, and one of them was, of course, CS161 that we are referring extensively. Berkeley professor David Wagner was also one of them, and there are many other people from IBM and many places. And finally, of course, this slide, since I have taken from Berkeley, so it's same group set of people who are doing this course, so it's more pro towards what Berkeley did. But finally, the committee has decided to choose something called Rindell. Okay, this is done by two young scientists from Belgium. very young scientist, right? So, and this was picked up. Now, although it was not the best, but it was very good. I mean, best, of course, I mean, it's all argument, and people try to prove that their algorithm was better than this algorithm, but ultimately this was chosen. It turned out to be good so far. Nobody is able to brute force break it. Okay. The problem with DS was that it relatively short key, short block size. The block size is small. The original text you have to break into multiple blocks, and this causes inefficiency. If you do it all in software and there is no parallelism available, then it becomes very slow. Okay, and short key length. If key length is short, then obviously easy to break it. Okay, so there is less security. And of course, DES become 3 times DES, but it was slow. Because 3 times you're repeating the same function, then it will become slow. Then came AES. It's the most widely used cipher today. Now it's being used in all protocols we know, right? IPsec, TLS, like even whatever we are communicating now is using AES. Okay, key size is 128, 192, 256. Now the algorithm came out with so many choices, right? Okay, and block size is always 128 bits. Now it's a double of earlier block size, that in case of DES. Okay, so block size is always 28 regarding of the key size. It has nothing to do with key size, whether you choose 128, 192 or 256. Okay, all right, and it's efficient. It can be done in hardware and software. Now this thing already we know. In order to brute force 128-bit key in ordinary computer, it will take 30 trillion years, and space wise you do parallelism, then it will take 7 into 10^15 suns. So brute force wise, even 128 bits cannot be broken. Okay, and if you increase it to 256, then of course it's very difficult to break it. With most powerful computer, or millions or trillions of such computers cannot break it. So this is the architecture. You have 128 bit of plain text as an input, 128 bits of cipher text as output, and key could be 128, 192 or 256, depending on what you want to do or what you choose. Now note that if you choose key length of 128 bits, then number of rounds, internal rounds, like in case of DES we had 16 fixed rounds, but here AES it's 10 rounds, 192 bits, then 12 rounds, and 256 bits, 14 rounds. So internal rounds depend on the key length. Okay, this is the architecture. Okay, so if it's a 10 rounds, let's assume it has 10, we are choosing this one, key size of 128, and we have 10 rounds, then we can see input is 128 bit plain text, output is 128 bit ciphertext, key is 128 bits, and from that we generate subkeys. That we have seen that, in case of DES also we generate subkeys. We call these subkeys also as round keys, first round, second round, and so on and so forth, right? Now there is a first pre-round, which is nothing but permutation. Okay, uh, using some one first round key, and then there are remaining 10 rounds. Okay, so 1 to 10 rounds, say 10 rounds, and then there is a initial round. So this is the architecture. Okay, so now let's expand this. Okay, so this is a plain text of 128 bits. This is a key of 128 bits. From this we generate first subkey till K0, and then from K0 we have key addition layer, the first layer. We do is just do exclusive OR with this key. Whatever text we get, we do some transformation. This is called initial transformation or key addition layer functionality we do. and then rounds start after that. Okay, first round up to whatever number of rounds. Whether we are using a 10 round thing, then this becomes first round and this becomes 10th round. Oh, sorry, this is 10 minus 1, 9th round, and this becomes 10th round. Okay, and at the end of 10 rounds, we get ciphertext. Okay, note that the last round here is slightly different than different rounds. So here we don't do one function which is called a mix column function. Okay, we'll come to that little later. Okay, just remember that we are using, if you are using 128-bit key, then we are using 10 rounds, and before the first round we do some key transformation or add sub key, and then we do 10 rounds, and last round we remove one functionality. Okay, so now little bit of, so what is the advantage here? Instead of 16 rounds in DS, we are doing only smaller number of rounds. Okay, because note that in DS we are using only one half, the 32 bits for encryption. One half is not, other half is not, right? So AES consists of layers. This functionality that we do, we call them layers. Okay, so each layer manipulates all 128 bits of data path. Now data path is a word we use in computer architecture in general. So data path is where you have a data of 128 bits, it keeps moving, and every stage we do some function, some transformation, but same data moves further downwards, right? This is called data path, how data traverses. Now, so we call it, because here all 120 bits keeps coming down, okay, in multiple rounds, and within a round it goes to different functionality. All right, so basically each round excepting the last round has 4 layers, which is byte substitution layer, shift row layer, mixed column layer, and key addition layer. Okay, and last round does not have mixed column layer, right? It has only byte substitute, shift row, and key addition layer. Okay, all right, any question? Are you able to understand this? Please focus, right? If you read it from the book, you will take time, because you'll have to read 30-40 pages to understand what is being taught you today. All right, so now byte substitute, as we have seen in case of DES, is for confusion. Shift row and mixed columns are for diffusion. All right, and then we have key additional layer right in the beginning. Okay, this we call also key whitening. And we generate sub keys out of main key, which is 128-bit key. For example, we keep generating sub keys out of that. Okay, as we have seen here, this one, right? Okay, all right. These sub keys we also call as round keys. And now note that this round key is also 128 bits, same size as initial key. All right, now data that is 128 bits, that comes because data size remains, or block size remains constant. We call this state. Okay, it means that this data keeps moving down and the state keeps changing. Okay, now we represent them in terms of a array. Some state is called a state array, which is 4 by 4, and each one here, like A0 to A15, each one represents just 1 byte. Okay, so if you have A0 to A16, A15, you arrange them in this way, like this. Okay, so first byte comes here, second one here, because you're showing in the form of matrix. Okay, the first round, as we said, is key addition or sub key. We call that sub key operation. is a round key addition or sub key addition. So from main key, which is of say 128 bits, for example, or it could be 192 or 256, whatever you choose. If 128 bits, we have 10 rounds, and then from this key we generate keys, sub keys, right? We generate first sub key, which is of 128 bits, and we use this in round key function. And then first round we use the first key, second round we use the second sub key, and then 10th round we use 10th sub key if you are using this one. Any question? Okay. All right. Now what goes in here? We have seen what this function is, nothing but just exclusive OR. Exclusive OR of this and the plain text. What happens in key round 1? And all rounds are the same. Up to 9th round, only 10th round would be different. It goes something like here. This we have already discussed. Now this is cipher key, and from cipher key we generate sub keys. Okay. Now let's look only at this part, because this is decryption, inverse of this, right? So now we generate sub keys, okay, which is 128 bit. Okay, it's basically represented in terms of words, each word of 32 bits. Anyway, don't worry about it. Basically, just think this as a 128 bit. Okay, now this is a block here. First round, sorry, not block, this is the first round. First round we do byte substitution, we shift rows, we mix column, and then take sub key and then add round key using exclusive OR. And that goes to second round and so on and so forth. Third round, fourth round, up to 10th round. And 10th round we'll see we do only 3 functions: sub byte, shift rows, add key, but mix column is missing. Okay, so this is encryption, and decryption we do it similarly. So we will not discuss description, we just go through slides and you'll understand it. So we are here. This is the first round, a round, okay, up until the last round, so up to say first round up to 9th round. Okay, then each round consists of substitute byte, shift row, mix column, and add round key. Okay, now we'll look at this one, sub bytes. Now byte substitution we have also seen in case of DES. So this is the function of byte substitution. You get data from inside, okay, and you do the byte substitution. Okay, wherein each one here is 16 byte. All right. So now we are going to do byte substitution here. How we are going to do byte substitution? Using same substitution function. We should have some matrix. Okay, and then based on that we can do byte substitutions. Then what we do is look at what these contains of these. What is this? What is this here? And then from that we transform into say A0 to B0. Okay, so let's look at what this function is. What is this byte substitution is, right? Okay. All right. So we'll look at this in the next slide. Okay. So basically, when we say byte substitution, we are transforming this one into the one here, right? Okay. So 128 bits of input transforms into 128, but we are splitting this. Okay. So what we are doing now is that, so sub byte operation involves 16 independent byte to byte transformation. 16 into 8 gives you 128. bits, right? So our block is 128. So our block, input block is this one. Okay, we have created, original S0 to S16. Now we are writing, or A0 to S16, we are writing in terms of S00, S10, and so on and so forth. Okay, and this is transformation. This gives transformation function. We call it S box. So now if you have to transform one byte, for example, this byte here, which is 8 bits. So we can show this as a, in terms of hexadecimal X, Y. So X is 4 bits, first 4 bit, Y is next 4 bits. Now from this we take first 4 bits and define from that a row number, and take Y next 4 bits and take from that we define column number. At this point here, which is X, Y, and row X and column Y, we take this data out, which is again a byte. Now in case of DES, we have seen 6 bytes we are transforming into 4 bytes. Here we see that we are transforming 6 bits into 4 bits. Here we are transforming 8 bits into 8 bits. So now we, from this we take it and put it here. And so we do this thing for all of this. It is all 128 bits here, or 16 bytes. We transform to these 16 bytes here, 1 to 1. Okay, so for example, the one S00, we'll have to look it, we'll have to go appropriate column and row, and then for example, this belongs to S00, then this will go here. Any question? Are you able to understand it? Yes, no?
Yes, sir.
Okay. So byte substitution we have already discussed. So in software implementation, S box is usually realized as a lookup table. Very simple, right? Now please go through it. Byte substitution provides confusion, and then all these points we have already discussed. Okay, and when we do decryption, we do just inverse of that, right? So for example, we from this state we get this state after transformation, like this here, this to this. When we are decryption, we do opposite of that. Just a minute. Oh, all right. So this is a reverse for decryption. All right. So what we have discussed now, we have discussed S function. Now next two operations that we do, or two rows that we perform, is shift row and mix columns. And these are diffusion layer. Diffusion, we have seen that even if there is a 1 bit change, it results into many changes in the output, right? Okay, so how do we do this? So this output that we received from S block, we do shift rows and then mix columns. So we are here now into shift rows. What are we doing here? We got here 128 bits in terms of 16 bytes, which are put into a state form or matrix form. Okay, now what are we doing after this? Now we can see why we are putting it in this form, right? So now we are doing shifting of row. Okay, how are we doing it? So these are the rows, right? So what we are doing is that first row is unchanged. The first row here and first row, this input is output. The first row remains the same. You can see it is. Okay, can you please mute yourself? Okay, thank you. Okay, and then second row, we do 1 byte circular shift. So now this one here, second row, we just one byte we have shifted towards left. Okay, so this red here comes here. Now take the second row, then shift it by 2. So this red, first red will come here, and this yellow comes here, and so on forth. And then fourth row is shifted by 3. Okay, so as a result of that, what you get is, just a minute, this one is transformed into the one here. And when you're decrypting, just do inverse of this. Okay, same thing we have shown here. So exactly the same thing. What we have discussed here is go through this if you're not able to understand what we are doing using this diagram. Okay, so we have now done shift rows. Now next is mix column. Mix column is basically again for diffusion. So what we do is that we take this as an input and do matrix multiplication. Okay, it's very simple matrix multiplication. So multiply 4 by 4 matrix by other matrix. This is 4 by 1. Okay, and this result is here. Okay, so basically it transforms each column of state into a new column. Okay, so basically a single bit flip from S when fed to shift row and mix column. This is a mix column. Earlier was shift row. Then it results into, multiple bit flips in the output within single round. Okay, now you do this for 9 times. Okay, and of course in each round we have something called add round key, which is take the sub key ki and do the exclusive function from state information that is coming from top. Okay, all right, this is what we have done. Now sub keys are generated from the main key using key schedule. All right, now how do we do it? Please look at the slides or read it from the book. It's very simple function that's given. Okay, so this is all about AES round. Okay, you get the initial state, then you have do okay, so this is all about what happens in one round. Then substitution function, then you get a state, then you shift row you do, then you mix column, and then you add round key, and then you get the state, which is 128 bits transformed in one cycle or one round. Okay, and the last round, as we said, is slightly different because it does not have mixed column functionality. Rest of things are the same. Okay, now let's discuss in few minutes what is AES security. How can you prove that all this tamasha we have done works? Is there a theoretical proof available? Using, lemmas, proofs, whatever, mathematics? Answer is no. But it is secure? Yes. Can Eve looking at, 128 bits are given as plain text in the beginning, and then what you get is a 128 bits of encrypted text using AES. Eve looks at this, can she make out anything out of it? Answer is no. Okay, in last whatever years, now it's not 20 years but more than 20 years, nobody is able to break it. All right, so takeaway is that AE is more than standard block cipher algorithm, which is large enough to prevent any brute force attack. However, side channel attacks are possible. This word side channel we are introducing for the first time. The algorithm by itself is perfect, but if you screw up in implementing it, then you can do side channel attacks. Okay, so side channel attacks are basically the way you implement, and there's a weakness in that can be exploited. So there are side channel effects people have exploited for this algorithm, but it's nothing to do about the algorithm by itself. Okay, implementation is very simple. Now you see 128 bits are just moving from one layer to another layer and one round to another round. And so basically it's kind of pipeline that we are creating. If you study data, if you study computer architecture, you study the concept of pipeline. You'll see this beautiful system. So now we have commercial ASICs available, so you can do it at very fast pace. So AES is modern block cipher. All these things we have already studied. This can be efficiently done in hardware and software. Now, is it IND CPS secure? Anyone can answer this? Is it? Yes or no? Attempt. When we say block ciphers, we are talking about AES and DES both. And we are using the same key. Note that we are using the same key. Now, if you use the same key and same input text, it will result into exactly whatever. If you repeat this process multiple times, it's just one-to-one mapping, exactly same output you get. So anything that is deterministic, because key is the same, then it is, you can read all this, because now Eve can guess it, right? So block ciphers are not IND CPS secure. Note then in one time pad, this thing was coming because every time you were changing the key. All right, because I mean, Eve first sends M1, she knows she's sending M1, and then Bob or Alice replies with E of M1. Next time she sends M2, she receives E of M2, which is different from, because M2 is different, so E of M2 is different. Next, later on, she sends both, and then Alice picks up one of them, say M1, encrypts it and sends it back. What? E will receive E of M1, so she knows now that's something that she has sent earlier, so she can, with half probability, she can say that yes, I know it, it's M1. Okay, probability 0.05. So it's not IND CPS secure. And we have seen block ciphers. The problems now with block cipher. Block cipher, we say that we have stream of data or data, then split into block and use this AES or DES. Okay, then these are not IND CPS secure. That's the first problem. What is the second problem? Block ciphers can encrypt message of fixed size. This block size is fixed, 64 or 128. Okay, what happens if message is longer than 128 bits? Then you'll have to create multiple blocks and so on and so forth, right? All right. So these are the problems of block ciphers. Please go through this comparison between DES and AES. Okay, we already discussed all of this. All right. So that's all. Any question?
So I emailed you about the first assignment.
Just hold on.